Okay, now go.
Okay, you can see my slides?
Yeah.
Okay. My talk today is about MeasureDB database update for OH measures. And so I start with mentioning where we detect OH measures. So there are two main categories of OH measure sources with most significant number. It is single-stellar measures in AGB stars and also measures in star-forming regions. There are about 2,500 single-stellar OH measure objects known to date and about 1,000 measure sites in star-forming region. This is information from MeasureDB. Another categories of OH measures is external galaxies. Almost all are mega measures, and also supernova remnants, and very rare is OH measures in comets, but we will not focus on them. Regarding OH measures in circumstellar sources, I want to mention the great work of Dieter Angels in collecting OH measure observation of this kind of sources. So his database is collected using data starting from 1983 up to 2022. It is very nice and consists many observations for single-stellar OH measures. But what about star formation regions? For star formation regions, there is a work by Haihua Xiao. The team led by Xiao in 2014 collected very nice compilation of OH measures in star forming regions. And this paper was like a starting point for our collection. So we use it a lot. This is just compilation of what CSIRO catalog is. So they created a unified catalog containing data from 21 papers, not only ground state OH measure, but also excited state, starting from 4.7 gigahertz up to 13 gigahertz. So you can see in these slides the number of included papers, detections, and measure sites. So difference between detections and measure sites is that in one measure you can make many detection in different polarization, different frequencies. So that's why number of detection is larger. So what we want to do in this work, so we want to create the most complete database of OH measures in galactic star-forming regions that includes also latest surveys that is not included in CSIRO catalogs, but also less known surveys that also can be important in statistics. So we also decide not to only collect tabular data, but also extract maximum information from the papers, including non-detection data, spectral images, source descriptions, polarization data, mesospot data, and also magnetic field measurements. So this is almost all that you can need to extract from paper to study these kind of measures. There is aim of our work. So another important point is that database should be regularly updated, because if we publish database only once, for example, in Visual, then new survey will come out and database become outdated. So that's why we decided not to publish it in Visual, but instead we publish it in our information system called MeasureDB.net. And it can be actual to any time. So if new survey will come out, then we add it to MeasureDB, and you can always look at the up-to-date database. Also, aim of our work was to perform the statistical analysis of OH measure in star-forming regions in the same way that we do for methanol measures and water measures. So published in the previous papers. So in this slide, you can see the current status of our data entrance and comparison with the catalog of CSIRO of 2014. So you can see that number of detections increase almost 5 times. Number of measures increase almost 2.6 times. So this is quite significant improvement in statistics. And this is not only concerned about ground state OH measures, but also excited state. So we have increased 1.5 times in number of sources for excited state measures and also for detection. The reason for this increase is not only that new papers came out after work of CSIRO, but also less known surveys is included that is not included in work of CSIRO 2014. Here are some details on how we enter information into database. So we use special information system that is part of MeasureDB. We used data published in Visual for papers that have such information. If not, then we use PDF files or also supplement data published in at publisher. So we extract, as explained, detection, not detection data, interferometric measure spots, Zeeman splitting data, polarization, text decryption, and spectros. This is example screenshots of entering the data into MeasureDB. So you see that it's like a step-by-step process. When you enter information for each paper, enter CSV files, add semantics, and also split spectra to enter it to measure database. So it's not very complex process, and it is quite easy to use. So some of my students already use this information system to add information to database with me. And how we extract data from PDF files. This is maybe some technical detail, but maybe somebody interested. So we use tools like Tabular for CSV data extraction file reader. And for text description, we use machine learning service Grobit that convert PDF files to text. It is very useful for text extraction. And as I said, for image extraction, we split a large image set into individual spectra and add semantic information to each spectra. So here is some screenshots of MeasureDB information system that was developed almost 6 years ago, and currently one of the extensive resources with information for measure studies. So it decided not only to study the statistical parameters of measures, but also to study the individual sources. So you can see detailed information about any known measure object in the galaxy, and the measure database will show you the details, including spectra and list of literature that you can investigate further. So in the near future, we plan to integrate large language models like ChatGPT, because it is database can provide very good prompts for it to create AI-generated scientific reviews. So you can use it in maybe proposals or individual sole description of papers, but this is near future. So to the present, MeasureDB database contains information on all common measures in Stafford regions, including water, methanol, and OH. More rare species like ammonia and formaldehyde also included, but not complete. But common species are included at the level of 95% in terms of ratio of included detection to all detection in the literature. Papers that are currently not included in MeasureDB are individual studies of known sources, but they do not change the overall statistic of known measures. So they only complement the number of detections. So the overall picture can already can be analyzed with MeasureDB, And also, if some new survey will release, will be included in MesoDB, and still Meso will be actual. So if you know any surveys that you cannot find in MesoDB now, you can send me an email, and it can be solved quite quickly. So if you the new information can be added quite quick. So starting from 2019, 4 papers was already published regarding collecting and analyzing data from MesoDB. So in 2019, the database was first released. Then in 2020, we used the database to make a statistical research of methanol measures. In 2022, we released the water measure database. And also in 2022, we used water measure database to do extensive statistical research. And currently, the paper for OH measures is being prepared. So what you can hear in this presentation is likely to be included in this paper. So please stay tuned. So how we can use this measure database? So there are plenty of things you can do. And what we do with measure database. So first thing is correlation between measure flux and measure dust clump parameters. Second is predicting measure emission toward sources that is not observed. Then third is you can analyze physical offsets between dust clumps and measure position, so studying interferometric positions. You can analyze for measure variability, and you can analyze also sequence of star formation using measure, because each measure species have its own physical conditions that arise on different evolutionary sequence. So this is not complete. You can invent something new, and this is up to you. So we briefly go through all these sections, and the first one is correlation between OH measure and dust clump parameters. So what we do is quite a simple thing. You just cross-correlate between peak flux densities for OH measures and physical parameters of Atlas-Gale clumps. So we cross-correlate these two catalogs and look for correlations. So you can see that there are plenty of correlations. So we found correlation with column density, volume density, and surface density. If we use the Spearman correlation coefficient, it can be also include nonlinear characteristics. So we also see the correlation between dust temperature, clump luminosity, and luminosity to mass ratio, but they are not linear. Interesting that correlation at 1665 gigahertz is stronger than 16.7. There are some example plots of most strong correlation, so you can judge how they are, how real they are. The next thing that we do is we correlate the OH measure flux densities within each other. So we correlate different frequencies of OH measures. And we also find strong correlation between 7020 and 1667 megahertz. This is Pearson correlation. And also we find some nonlinear Spearman correlation with 6067 and 6065. And here are examples of correlation that you can judge how real it is. And so the next section that we do is predicting OH measure emission toward dust clumps using generalized linear models and also neural networks. So what is the motivation for this study is primarily the question, how many OH measures we know in the galaxy. So for example, in the central part of the galaxy, I mean central plus minus 60 degrees, there are approximately 7,000 Atlas-Gale sources, with flux more than 0.4 Janskis, but only 400 sources was observed in OH transition, I mean 1665. But what about the rest? How many OH measures are there? So to answer this question statistically, we use two approaches. We created the train sample from MeasureDB, where non-detection and non-detection are stored, and also using blind survey, we store the sources that was not detected. So in this case, blind surveys is ideal for training, because you know that in each source that AtlasGal don't have detection, it can be used for training as non-detection, because blind survey will not miss anything, only in terms of sensitivity. So we use two approaches. First one is more simple, is generalized linear models, and second one is neural networks. So GLMs give accuracy like 50–70% of prediction, and neural networks give much higher accuracy of 70–90%. So what we can do with such models? So if we have such model, we can say how many measures are approximately in the galaxy, and maybe create some target list for further OH measure targeted surveys, or compare with blind surveys that soon come out. Here example of what we have in output for GLM and neural networks. So for GLM, you have a linear formula containing physical parameters of AtlasGal clumps, and as output you have probability of measure detection. So you can easily calculate probability to any AtlasGal source with defined physical parameters using this model. So if you assume some threshold like 0.5, what is higher is probably detection, lower is non-detection. For neural networks, it's quite more complex. So you don't have such formula, because neural networks is not deterministic, but also you can predict measure emission in any source using physical parameters as input. So what we found that neural networks give much higher accuracy in prediction. So in this plot, the x-axis is variation of assumed threshold. The y-axis is relative number of missing detection. So lower is better. While GLM predict only approximately 50%, or miss approximately 50% of sources, neural networks predict almost 90% of sources. This is a very good result and can be used for further prediction. Yeah. So for this task, the blind surveys is ideal. So we're waiting for new blind surveys like GasCap OH, and this can dramatically increase the quality of prediction of OH measures. And training samples should be prepared very carefully, because it's very sensitive to detection and non-detection. If you provide wrong training set, the model also be wrong. And this, with large training sample, we can also investigate how many measures have OH measure, and that's mean how many measures are in late stage of evolution, because OH measure arise at late stage of evolution. The third, what we can do with MeasureDB is analysis of physical offsets between OH measures and clump dust position. So if you go to MeasureDB, you can see the special mode use only interferometric data. And if you check this mode, you can work with interferometric positions. No single digit data is used in this mode, and you can study the position of measure in comparison, for example, to AtlasGal sources. So in previous work, we analyzed methanol interferometric position, and we found that class 2 methanol measures is much closer to position of peak Atlas Gal position, but class 1 sources is much far away. So this is consistent with the theory when the class 2 methanol measures are pumped by infrared radiation in the circumstellar disk and inner part of outflows, and class 1 measures are pumped by collisions, and it is found in distant parts of outflows. So we repeat this analysis for OH measures, also for H2 measures, and what we found that there is no statistical difference between OH and class 2 methanol and H2. So all these three species come from the same place, and only class 1 measures is far away. So this is statistically confirmed by Kolmogorov-Smirnov test. So this is in agreement with previous studies. For example, James Caswell measured positions of 200 measure sites, and he found the same thing. But now we confirm it with a larger statistic of more than 300 sources. Next, what we can do is analyze OH measure variability. So there is also special mode in MesoDB that you can study the measure variability. And we use the classical definition of variability index is ratio of maximum to minimum flux. But the problem is that our database contained data from different telescopes, different observed epochs. So we have to deal somehow with it. So we do not include sources with position shift larger than 40 arcseconds. We also do not include interferometric flux in this analysis because it can be missed, of course. And we only analyze sources with minimum 50 sources that have enough data to compare variability. And this is preliminary result, and we see that OH measures and 1665 megahertz, it's more variable than other frequencies. But this is very preliminary. It should be more detailed analysis. The final thing that we do with measure database is analyzing the evolutionary trends in star formation regions using OH molecule. So I don't have many time to explain the details of each stage of star formation, but I can say in brief that different measure species appear at different evolutionary stages. So OH measures seems to appear at late stage of star evolution, where ultra-compact H2 region forms. In 2022 paper, we do such analysis, and we analyze luminosity to mass ratio of Atlas Gal sources and look what measure species associated with which values of luminosity to mass ratio. And that's what we get. This is our previous result. We have found that OH measures appears at very early stage of star formation, and OH measure appear at very late stage. This is in accordance with the theory. What we do now? So we try different OH measure frequencies, and maybe different frequencies appear at different evolutionary stage, because, for example, for OH measures or for methanol measures, 12 methanol measures appear at later stage that 6.7 gigahertz. So maybe something happened also with OH. But we found that no. So all measure transitions appear relatively on the same stage. So we don't see any difference between different transitions. So maybe that's a good result, because it's much more simple that different frequencies can appear on the same stage. And also, I want to mention that I want to clarify that MesoDB is open to anybody without any restrictions and any limited access. So you can even download all the data in CSV format and do the research using your favorite tools like Aladdin or TopCat. So we're looking in the future. So we're planning to finish data entrance till the end of this year. The data entries include also ZMAN splitting data and also individual studies. We also plan to create automatically generated prompts for large language models like ChatGPT, so you can use it to create text literature review of the sources with data from MazerDB. Because if you now try to ask some ChatGPT information about this, you can get only general information, not specific. But with this information, you can get very nice scientific reviews that it can be used in proposals. And we also keeping eye on new meta surveys, for example, escape.ph, very look forward to it. And also for other large-scale surveys like Meerkat, SK, and we are looking for it. It can dramatically improve the number of known OH measures. Okay, thank you very much. And any questions if you like.
Thank you so much. Excuse me. Thank you so much for that talk, Dmitry, and thank you for putting together such a rich database. I know I use it all the time. It really is fabulous. Yeah, if any of you are interested in Mazers, or even if you're not interested in Mazers and you think there might be one in your data, go have a look. It probably is in the database. So thank you so much for the work that you do, and all this analysis is super interesting. I'm always learning new stuff about Mazers, and I feel really out of depth, but thank you very much. Do we
You're
have
welcome.
any, oh, thank you. Do we have any questions for Dmitry? Andre?
Yes. I just want to start any discussion. The first is thing that Dmitry said that everybody can provide some input for the database. In this case, I would ask if you really check the references which are given in the database, and if you can add something that will be very helpful. But for me, as interesting, the question is about details. When you say about the difference in positions of OH Mazers and Atlas Gal sources, is this different for different transitions, or all positions are the same for the Mazers, for OH Mazers, the different frequencies interferometrically?
I understand the question, and currently I do not do such analysis, but it can be quite easily done. And what we do is comparison with Atlas Gal, but I think we have enough data to compare transistors with each other, so it can be done. So I still do not do it, but it can be done. Yeah.
Because 1720 are associated with supernova remnants and other things, while the others, so one can expect that they have different positions at different frequencies. Is that correct? Just your opinion. Did you see this?
I see the quite large spread of positions in different frequencies, so I think it's correct.
And other question, I know that interferometric positions which are obtained by different instruments can differ, and for quite a bit, just for even for tens of arc seconds or something like that. Is this the case with OH Mazers, or you didn't notice this? I saw this for methanol once.
You mean absolute positions, yeah?
Yes, of course, because
Yeah.
Atlas Gal positions are absolute positions.
Yes. Actually, this just increase the spread, but in main conclusion do not change. So if, for example, so one or two papers has some shifts in position, of course, this affects the statistic, but overall is not changed.
Thank you.
Okay.
Max?
Yeah, well, just trying to respond to Andrei's point. Like, if it comes to tens of arc seconds for interferometer, I think we should check, and we probably can discuss individual sources. But when it comes to sort of arc second and below, even for like connected interferometers, then issues like systematics will come at play, because ultimately, well, if everything is ideal technically and the position should only be limited by signal to noise, but in practice it doesn't happen. And we have other effects, and we have ionosphere at low frequency and this kind of thing. And if there is one-off observation, like is typical for many surveys, then essentially it's often difficult even to assess what the actual accuracy was. So when it comes down to this sort of sub-arc second level. And I think even people publishing individual papers, they wouldn't be putting this information. At best, they can just pass whatever observatory staff told them what that level of, say, astrometrical accuracy is likely to be. We're still finding issues with ASCAP that sometimes, I don't know, ionosphere was in a bad state and we have like little bit worse positional accuracy in some parts of our field and things like that. So that information, I guess, would be extremely difficult to take into account unless someone would go and like one by one case or observe the same field over and over again and see the differences, which is difficult to do. And of course, in current world. So yeah, it's a tricky business, but tens of arc seconds or arc minutes, there could be some, I don't know, errors, or even very typical for interferometry, for example, is people may self-calibrate, which will kill the absolute position. And well, hopefully they will write about it. If someone is interested only in like relative position of the spots, it doesn't matter. But if people are interested in the absolute positions, then they have to be careful with this thing. Yeah, that's what I want to add for this point. I guess in a database, it would be interesting to try to capture this information, but if the authors don't provide it and observatories even don't provide it, then I think there is limited number of things we can do, except if we notice something strange, just go back and investigate.
Yeah, I want also to mention that these things, when the source positions is shifted a lot, like tenths or second, it can be easily catched with MesDB because we used source grouping. So if we group many observations of one source and some observations go away, so we can easily catch them and say, okay, this is something wrong with it. So mainly these things can be done with MesDB, but this analysis should be done very carefully.
Okay, Anita, so it looks that we turned on to discussion. Is that okay?
Oh yeah, that's fine. That's fine. We're not terribly formal here. It's all good.
Yeah, so the questions which were raised by Maxime also I have such a question. If the Zeeman pairs are identified, yes, even by interferometry, I see that the positions of Zeeman pairs in LCP and RCP are quite different. How this can be explained, and how can you really identify Zeeman pairs interferometrically? Because this is the very important question. Maxime, can you answer or provide some
Yeah,
insight?
well, I think at that level, probably every source has to be investigated in detail. I understand what you are talking about, and probably maybe it's a good sort of project. If you have like one source or few sources where it would be nice to check it in like every detail possible, we can think of some projects, say at Compact Array. and basically see where it goes from there. So I think at some level it will be difficult to say, but you know, if we try to observe that source, say, multiple times, we may get a feel of the error. I would say things for compact array in particular, if positions are larger than, say, half arc second, most likely it's a real separation. If it's below that, then a lot of things can be at play. Having said that, for like things which are close within the same beam, same observation, same instrument, like same setup, the majority of these effects should be the same. So yeah, if we just compare two positions, one with respect to each other, like of two components detected in the same observation simultaneously, yeah, I would have a tendency to trust them unless there is a very low signal to noise or something like that. But for like very strong sources, I just don't see any effect which would be causing this different position unless something was really stuffed up during the observation. Yeah, but it's hard to imagine like what would give a different position of something co-observed together. Having said that, sometimes interferometers throw a surprise to us. Like if you do something over and over again, you see that sometimes some strange effects we never thought about creep in. But yeah, I would say like, you know, let's select some targets and look in detail.
The first paper for determination of, for example, of Zeeman pairs by Carl Menton, which I saw what for W3OH, and the difference in RCP and LCP interferometric points, positions, was about half the source itself. So how do they think that these are really Zeeman pair? And I don't really know. Maybe Busaba knows the cases when we really see that the Zeeman pair in LCP and RCP came from the same position, exactly the same position, with the positional accuracy. Can you just comment on that?
Yeah. Yeah, I would like to add, with following your question, really, I think it would be useful, you know, with this potential Zeeman pair that we think that they are in from the single dish observation, certainly should be really proved by VLBI measurement, because I think from even for the CSIRO sources, you know, some brightest source, you know, the brightest feature that we saw, maybe not a single spot. Yeah, from my experience or several sources that we have been mapped with Merlin and with LBA, or you also seen the several VLBA observation by Fish et al. Yeah, I think several sources is turned out that is multiple sources there. Yeah. So I would say that, you know, the database or the new sources that Dmitry has been listed as a potential Zeeman pair, if we could add the information there that, okay, these sources already prove that they're real Zeeman pair, I think that would be great. And also the new sources that we think that is a potential Zeeman pair should be a new project. Yeah, that should be investigated with VLBI. Yeah, thank you.
Can you provide any good example that the Zeeman pair is really identified interferometrically? Because a lot of people they just determine they measure LCP, RCP with with single dish and make quite firm and interesting conclusions. But I didn't see, maybe I'm negligible about that, but I didn't see any convincing example for them.
Yeah, I think that there are many, quite a few papers that we did, you know, map all those Zeeman pairs. And for example, I think ideally, I think Malcolm can also add a comment on that, you know, if we can map this Zeeman, normally for the Zeeman pair, LCP and RCP, they should have the same, you know, if we can map with full Stokes polarization, you can really identify, you know, with the projected magnetic field or electric field direction should be similar. You know, I think Malcolm, we can add to that, you know, or we could even detect the Zeeman triplet. However, the pi component of the Zeeman splitting is very rare. So I only detect with Merlin, it was the first Zeeman triplet that we did detect with all these three, you know, you say that the three lines shown at the same position within the position accuracy with of the instrument at that time is Merlin. And then later Fish et al. Also remapped the same source, and they found that it's actually from, it's not exactly the same, but you can say that within the, you know, the, how you say that, the resolution or the clump of the meso. So the behavior of these three meso clump, you know, match and convince us that they are the Zeeman triplet. And also another evidence that can be done, even though if you don't have VLBI measurement, by having observation of the other line. For example, if we have 1665, candidate for the Zeeman pair, if we can observe them in 1667, it should have a less splitting. So that can be also evidence that can support. And even also if you have 1720, so that can be done, to confirm. However, I think I would say that to be 100% sure, I think follow-up observation with VLBI would be really useful. Yeah.
So sorry, Pusaba, why follow up? That means that that the measures are changing. So we should see something exceptional, or follow up is just the same. Maybe it is reasonable to make at the same time simultaneous observations with VLBI and single dish, but VLBI provides this possibility.
Yeah, indeed.
As I understand.
In general, I would say most of the sources, most of the OH measures they are not so how to say that, so fast variability, especially in a star forming region. You know, even though, for example, in one of the sources, like for the W75 North, even though Fish, I think, observed them even, I think, 0 years later, they still detect, you know, the same feature. I would say cluster. Yeah, the same meso cloud that you can identify the velocity and the position. Yeah. Unless there are quite a few sources that very high variability, that will be difficult. Yeah.
So you think it is good to for new effort to do something like that, like what Maxime was talking about. So it is worth doing that in future. Yeah.
Yes, indeed. Especially now we have a new telescope coming up in Thailand, the 40 meter, that will also operate in L-band. And hopefully for some sources, you know, we can collaborate with parks if we have, you know, the LBA, of course, can do it. And also in East Asia, increasing more telescope in L-band. I think we can do VLBI on more sources to get a position. I'm not sure about full polarization. Full polarization will be difficult, but at least you can, with dual polarization, you can actually identify, you know, those LCP and RCP, whether they are the same position with phase referencing. Yeah.
And still, I have question to Malcolm, for example. Malcolm, are you here?
Yeah, I'm here.
Yeah.
Nice to hear you. So Pusaba raised very interesting question. Sorry, Anita, that I'm taking too much for this discussion, but that Malcolm, that if we see LCP and RCP, and can the images of masers be different in LCP and RCP? Because the maser image, like Busaba already mentioned, it is not a point, not a point. It is not just one delta function or something like that. And as it was also shown by Lisa Harvey-Smith, that there can be extended maser emission, and we've seen also that the different velocities, for example, it was done with Imai, Hiroshi Imai-san, for S269, that the image at different velocities is different. So can this be seen in the hydroxyl masers, that the image can be different at different polarizations? What do you think? You are a best expert on this in theory.
Well, I think certainly in the observations that we published back in 2004, we checked for Zeeman pairs, and it required some sort of spatial proximity for the left and right images. I think that there can be sort of slightly different left and right beams, for example. That I'm not sure how large the effect would be though in shifting in L-band. That sort of.
These things are observed almost simultaneously and with the same instrument, and we can compare some images. So what do we need? Do we need VLBA for that, or ATCA is okay?
Well, yeah, VLBA can do it for sure. Yeah. I mean, and probably most of the modern instruments could do it. EVN can do it as well.
And there will be no technical issues in this case.
Ooh, don't know about that.
Cool. Well, we might just at least pause things there with this discussion. I hate to interrupt a rolling discussion, but we have one more speaker that we'd like to hear from. Jay, are you there?
Yeah, I'm here.
There he is. Hi, Jay. Would you like to start your presentation for us?
Yep, cool. Just give me a second. Let me share my screen. Hopefully doing this. Hopefully you can see it. And then if I go like this, continue to share. Yeah, okay. You guys can see it?
Yep.
Yeah, cool. I'll just go over here. Cool. Well, thank you so much to the SOCs for giving me a chance to talk about my potential science idea, or it'll be interesting. I think. Cool. So what I want to talk about is how the potentiality of doing VLBI astrometry with OH masers from the southern hemisphere, and the main target is to just figuring out or revealing or mapping the Milky Way from the southern hemisphere. So interesting. Oh, good. Before starting, I would like to begin by acknowledging the Walamatugal people of the traditional owners of the land that I am meeting from, to all of you today, and pay my respects to elders past, present, and emerging. Okay, I just wanted to use this opportunity to introduce myself as well, and why not? So hello everyone, my name is Jay. Currently I'm at postdoc in GasCap OS project, which I will talk about a bit later on as well, in CSIRO over here at Australia. my research experience, it's been almost like 7-8 years that I've been in major astronomy or VLBI, spectral line astronomy. I'll similarly, like Anita loves CLIP, I love majors. I'm in all forms, in all styles, I love majors. So I've done work with major emissions in high star forming regions. I have experience with major flaring events or outburst in high mass star forming regions. I've done work in making high resolution VLBI maps of the major sports. I've done VLBI spectral line astronomy, which is what I'm going to talk about in this talk, which again corresponds to the Milky Way structure, mostly from the southern hemisphere. I got experience in data reduction and analysis of all three main major species, if I can call it that, 22 gigahertz water majors, 6.7 gigahertz methanol majors, and recently in my postdoc is 1.6 gigahertz hydroxyl majors. Just to going a bit more into what I've done, which is I think is a main. I think it's good so that it makes sense later on why I am talking about what I'm talking about in my talk. So on the left hand side, you see you see one of the major flaring events in the NGC 6334 high mass star forming region, and at the top plot is the major sport map, and the bottom is the velocity spectra. So the plot in the middle is the internal motions of the majors. This is G10 and G24 as the label suggests, and these are both water majors. So I have done work in the measuring the internal motions of the different major sports in a in a cloud. On the right hand side is what most of my research work has been dominated from, is doing the astrometry, VLBI astrometry, with both water majors as well as the methanol majors. So these are some I think top one is really cool curve, if you can get that sort of parallax curve. So the upper panel and the bottom panel, the 3 rows or 3 columns in the upper panel represents the sky motion, the proper motions in RA and DEC, and the parallax signature in RA and DEC. And I will go in my talk what I mean by parallax for those who are, I'm pretty sure all of us know, but in case those who don't, yeah. Cool. So it was in 2023 at the start, in Feb of 2023, I attended a workshop in Netherlands, which is called Lawrence Center workshop. It was titled Mapping the Milky Way. There's so this group is I think mostly they're blend of people who are doing Milky Way or studying the Milky Way structure, and the people from the different gas surveys, or people studying sapphires, or people like me who are studying who are doing parallax to high mass star forming regions. And what they take out from that conference is a map like that. Is what you see on the left hand side is the Milky Way map, which includes all of these inputs. This map is it's from 2022, because the most recent map hasn't been available yet, or I might have not able to manage to find it. So that's the most accurate Milky Way map looks like. That's what it looks like, and this comes from Reed and Zhang et al. In Science in 2020. Okay, let's just focus on this particular map. That's our sun. That's where we are. These are the 4 quadrants in our Milky Way. Now, I'll talk about the Bessel survey, which is the bar and spiral structure legacy survey. That survey is aimed at studying the spiral structure and kinematics of the Milky Way, spiral structure, and as well as the galactic bar as well. That's why the bar and the spiral structure. How do they study that? They study it by measuring distances via trigonometric parallaxes to high mass star forming regions in the Milky Way. What are their target sources? The targets are methanol and water majors that are associated with young high mass star forming regions and compact H2 regions. So a perfect tool to target these high mass star forming regions. And so I'll talk a bit more about that as well later on. And this map over here, it's over projection of that Reed et al. 2019 model, which shows around more than 200 trigonometric parallaxes, which comes from not only from the Basel survey, but the similar survey that in Japan is done by Miriki Honma-san and his team, the Vira survey, and Hiroshi Imai-san is here, and his parallaxes might be will be in this in plot as well. Okay, so that's and these arms that go over, that's what the what do you maybe I'll talk about it later on. Cool. First, I'll talk about the trigonometric parallax. So it's just basic, simple, class 10 geometry or physics, you can say, is that if you can see my cursor, so it's sun over here, so that's Earth over here. Earth, it's full rotation. So if it's in December, it's over here. In 6 months, it'll be in June. And looking at a particular star as compared to relative to a distant background. And so we look at that particular object in 6 months apart, and the half of the angle that we observe, that's what's called parallax. And we know this distance from very accurately from Earth to Sun, and we know this angle, so we can calculate this particular distance, and that's your trigonometric parallax technique. Over here, if you can see my cursor, and please, Anita, do let me know if you can't see my cursor, is how the source looks like that's the sky motion. This is the motion in RA and DEC, and so from the sky motion you subtract proper motion, as well as then there's parallax signature. So if you see such a awesome parallax signature with such a small uncertainty, you'll be really happy, and especially if you can see it in DEC, because it's really hard to see parallax signature in DEC. Okay, now the main crux, whys, or some whys that I'm going to talk about. Okay, why bother about Milky Way structure? I have had this conversation with a couple of people. It's why? So it's, first of all, it's our home. Don't we want to know more about how our Milky Way looks like? How what's the scale? It's good to study the our galaxy. The other thing which my people that I talk to, or people who care about Milky Way structure is talked about, is that it's a local laboratory. It's every phenomena that we see in other galaxies. If we see that in our galaxy, it's first to test that. It's first to test things in our own home, and better improve on the techniques that how we test particular things, and then go out and then it becomes a benchmark for other galaxies to see the same astronomical phenomena. So that's why the Milky Way structure is really important. Why measuring distances? Why we care about distances in in galaxy? So it's the first step on the ladder to understand any astronomical phenomena. I'm pretty sure all of us know that almost all the measurement or calculations that we are doing, it's very important to have a distance to that particular source or that particular object, or wherever you are pointing your telescopes to. I think there's one very awesome line that I read from somewhere, is that what's the difference between astronomy and astrophysics? Astronomy is knowing the distance to that phenomena that you are studying. That in very simple terms, that separates out astronomy and astrophysics. So distances becomes very important. Why use trigonometric parallax technique to measure your distances? It's a golden standard of distance measurements. It does not include any priors. It's a direct measurement. You just point at the telescopes, basic simple trigonometry, and then you get your distances out. There's no need to any prior informations at all. So that's why any other distance measurements, whether it's standard candles or kinematic distances, they have their priors involved in them. So that's why trigonometric parallaxes becomes this technique becomes so important while measuring distances. Okay, why high mass star forming region? If I care about Milky Way structure, why I'm studying high mass star forming regions? Because high mass star forming regions when they are getting born, they are getting born at the heart of these spiral arms. So, and there's dense gases and clouds, and that's where the high mass star formation is happening. And as the star evolves, gets older and older, it tends to move out from the spiral arms. So it's the perfect high mass star forming regions, or tracking these high mass star forming regions is the best way to measure these spiral arms. If we track enough high mass stars, we can trace that particular spiral arm. Okay, why choose majors as your target? That's really awesome question if somebody asks that. The reason is that majors, same way as spiral arms, high mass stars forming regions are perfect tool for tracing spiral arms. Majors are perfect tool for tracing high mass star forming regions. Some specific major transitions, which I'm going to talk about, which are exclusively associated with the high mass star forming regions when they are getting born, when they are very young. So if we can track these major transitions, and that's why we can track those high mass star forming regions. They're perfect tool to do VLBI astrometry. They're very compact. Generally, you can find very bright sources. They do not disappear because we need to go observe something in 1.5 year time scale or something like that. So that makes them perfect tool for doing VLBI astrometry with them. So that thing is there even after you go after 1 year over there. So that's this map again. What do you notice in this map? Okay, I'll put it over here. So this highlighted region over here in sort of fade green, it represents the it's the rough estimation of the what you can see or what the telescopes can see from the northern hemisphere. And I've taken liberty with the coverage. So if it's plus minus something, please forgive me on that. But roughly for the VLBI and the accuracies that we're after, this is basically what you can access from the northern hemisphere. And all these data points that you see in this map, they all come from the northern hemisphere. What else you see? You see that this particular region is hardly have any parallax measurements. So all these spiral arms, how the spiral arms looks like from here, they come from other surveys, gas surveys. There are no direct parallax high mass star forming parallax measurements to high mass star forming regions over here. So far, I think there's only I'll say four published parallax measurements. There's been my team has been in Hobart who I was working with, have done few more parallax measurements. I have done some of them, but they aren't published at the moment. But at the moment, there's only 4 published from the southern hemisphere as compared to 220 from northern hemisphere. So though we think that we know so much about from the southern hemisphere spiral arms and how how the outer arm goes, where does it ends, where it doesn't end, but we are not actually sure. One of the other reasons that we are not very sure about is the inner Milky Way structure, because so much of inner Milky Way structure, either it's from northern hemisphere, it's very hard to get in those because the declination gets very low. So there's always that plays a role in your accuracy. So much of the inner Milky Way is accessible from the southern hemispheres. So this is the range. What I put down in fade blue color is what it's accessible from the southern hemisphere for the VLBI astrometry, and it's perfect. It's covers so much of our galaxy, and and we hardly have any data from here. So there's one more why southern hemisphere is crucial. Southern hemisphere is crucial because it covers so much of our Milky Way, which we can't access from the northern hemisphere, which includes galactic bar, galactic center. I mean, of course, you can observe galactic center from the northern hemisphere as well. And these arms. Okay, now what are the challenges in southern major astrometry? There's very few dedicated. Very first is dedicated spectral line VLBI teams over here. I might be mistaken, but I think it's only my team that has been working on the VLBI astrometry as far as the major astrometry goes from the southern hemisphere, at least in Australia. limited resources. There are very less number of dedicated VLBI stations, and their availability, like, you know, US had VIRA, which is like a homogeneous array, which is dedicated to do astrometry. Japan had like, you know, this sorry, US has VLBA, Japan has VERA, but in Southern Hemisphere we have LBA, but LBA comes with its limitations, and there's always questions about availability. Though I'm sitting in CSIRO, so I should not be talking too much. Like, you know, LBA is good. If any CSIRO person is listening. Cool. Finding suitable targets. So finding perfect targets, whether it either it's the target as well as the calibrators for the target, it's always a challenge that we have to deal with when you're looking for particular sources or going to particular regions in the Milky Way. Calibration techniques were also a limitations, that how like, you know, accurately you can calibrate the ionosphere, how accurately you can calibrate the troposphere, and it also depends on what frequency that you are dealing with. So that's also plays a big role in the, like, you know, VLBI major astrometry. Okay, now the main crux of the question, why I'm suggesting to do, like, you know, OH major astrometry, why this is OH major astrometry is crucial. First of all, it suits much better, I will say, for the current and upcoming southern VLBI resources. As you are all, these are the current VLBI stations at the moment. This is Hobart, where John is joining us. There's Saduna, Yagadi, Catherine. These are like, you know, again, ATNF telescopes, which is Parkes, ATCA, and MOPRA. This is Warkworth in New Zealand. Hopefully at some point SCAF, there's been, like, you know, big push to convert SCAF into one of the VLBI stations. SCAF has range up to goes up to 1.5 gigahertz, no, sorry, 1.8 gigahertz. SK mid is coming up in South Africa, which has that frequency ranges. And since there's TNRT people over here as well, so there's TNRT telescopes, which in the talks on Monday have been confirmed that L-band is working and they have done fringe tests. So it's perfect to do, like, it's available to do VLBI. So looking at future, it looks like with SCAP, especially with the SK mid and SCAP becoming operational into VLBI, pipe VLBI array, that will be a awesome improvement in terms of like, you know, our sensitivity and the coverage and the like, you know, resolution as well. So it suits so much well to for OH majors to use, or, like, you know, to use 1.6 gigahertz frequency range to do OH major astrometry over here. Okay. The second one is new calibration advancements makes a good choice for VLBI astrometry. So this is something that I worked on with my group at Hobart, where instead of doing the standard phase referencing, we are doing multi-view phase referencing. A lot of you guys over here know about multi-view phase referencing. On the left-hand side is a figure from the Reed et al. 2022, 2022-03. Yeah, where instead of what we are doing is that, so on the right-hand side, you see a plot from the Dr. Lucas Highland, who's at Utah's in Hobart. And in his PhD, he worked on this multi-view referencing technique. It's been, we know about this since 1997. Maria Roja and Richard Dawson in Perth has done a lot of work over here. So at the center, there's the target, which is one of your measures. And then instead of just, like, you know, having one or two calibrators and having them in a like, you know, linear, so you try to have it, like, in a straight line, so that it's easier to do like, you know, in interpolate, like, you know, calculate phases in linear way. What we do is that we try to have more calibrator sources, and I think at 6.7 gigahertz we can go up to there's different rings. Like, the first ring, this is, I think, up to 2 degrees. The second one goes up to 5 degrees or something like that. And we have achieved 10 micro arc second level of accuracy. So what happens is that instead of fitting a straight line, what we are doing is, so assume that your target is at the center, and these are your calibrators. At the moment over here, there are 4. So for every integration, you fit a plane instead of fitting a line. And in that plane, you sort of you figure out that what would be the phase at the center of your plane, and that will be the phase for your target, and you extract that phase, and then you apply those phases. So this is the phase referencing technique, multi-view, because it's using multiple calibrators. So this advancement has resulted with the Utah's telescopes, which is 4 or 5 telescopes, which I talked about earlier on. Almost similar matching astrometric accuracies as the VLBA has got in the Bessel survey. So that's a huge achievement, or to having that accuracies. That means we can go further into the Milky Way and look at the sources which are far away from us. And the result of that, this is one of the sources that I worked on, is the multi-view phase referencing. It's the same, it's the data comes from that observations that we've done using the Utah's telescopes. And over here you see this is the sky motion, this is the motion in RA and DEC, and this is parallax signature. And based on so when we assign a particular source to a particular spiral arm, we look at how the source, what's the distance it gives, and then how this source fits well with this LV diagram. So these this LV diagram and these spiral arms, these comes from the Reed and Tom Dame et al. 2016 paper, where they're using all the data available to them. They are using their own math to figuring out to choke out these spiral arms in the LV diagram. So 2 of the sources that I worked on and I got parallaxes, they fit very well with the inner Centaurus arm, and they're placed in those arms over here. As you can see, this is my PhD work. The difference that I want to show you over here, this source actually has a prior parallax that was done by Vasant Krishnan, again using the LBA, but instead of multi-view, he used standard phase reference technique, and his parallax was 0.48 plus minus 0.08 milliarc seconds. So his accuracy was 80 micro arc seconds. I got similar parallax results within the errors, but my accuracy is 20 arc seconds. So astrometric accuracy got 4 times better with using phase referencing with respect to the multi-view technique. So that shows that the strength of multi-view using the multi-view. Okay, good. So that's the calibration techniques. The third and fourth one is the suits better for finding suitable calibrator sources and even the target sources as well. Why do I say that? So we all know, we know that the lower we go in frequencies, the calibrators are much more brighter. So brighter calibrators always helps if you're doing astrometry. There are some challenges as well, which I'm avoiding, and I'll talk about later on. But calibrators getting more brighter is really awesome if you're doing astrometry. And number of targets that gets available to you. Okay, so this is one of the regions that I worked on during my PhD. This is the same image that you have seen before. I'm just zooming in that inner Milky Way region. What I want to focus your attention is towards these yellow circular arms, which we earlier used to call expanding 3 kiloparsec arms. So, but my results, which is me with my colleagues, we published a paper 3-4 months back, which we have shown that the expanding 3 kiloparsec arms are actually not spiral arms. They are the part of the outer orbits of the galactic bar, which also are called as X1 orbits. So that's what we have found. These dots over here represents these parallax measurements to star forming regions. 3 of these parallax measurements have done by me. These arrow represents the galactocentric velocities, and I fit a very simple model of the concentric elliptical orbits, which are the are the bar or family of bar orbits in our galaxy. So I'll just stop for this one over here, because if you want to know more about it, please go read this paper. Cool. Okay, so when you look at this particular, so on the left hand side you see the same plot. On the right hand side you see the same region in the galactic longitude, but you look at it in the LV diagram, and these are the same major spots that you see, which we have got parallaxes to. And this red circle, that red ellipse over here, and this red square over here represents the region which there's been no parallax measurements. So in LV diagram, you look it over here, and this is the only region which is very clearly visible, which is what people earlier, that's where the whole 3 kiloparsec arm started from. But you look on the left hand side and you see there's no parallax measurements. Why there's no parallax measurements? Because this region isn't accessible from the southern hemisphere at all. It's northern hemisphere. So where it is accessible from? Southern hemisphere, but nobody has tried to do astrometry from the southern hemisphere in this region. Okay, I'll go a bit further over here. So this is the same region. That's the same area in the LV diagram, and I'm plotting over here is the number of observed or detected major transitions. If I'm pretty sure, I think the pink one represents the methanol majors, and the cyan one represents the water majors. And this comes from the glow star survey. Andreas Bremthaler in Max Planck, Germany, shared this image with me. And this LV diagram, it's integrated over plus minus 1 degree of galactic latitude, and you can see the LSR velocity as well as the galactic longitude. So you see that there are sources over here which falls in that particular region, which I'm super interested and want to do more parallaxes on. But if I go more deep and look at each particular target measure and then try to find its calibrators, it's suddenly you start rejecting sources that, okay, this source isn't good because there's no good calibrator, or this source is weak. And also there's a lot of things that goes when you're selecting sources. If you're spending 2 years of your telescope time on something, you want to be perfectly sure that everything is all right. Okay, on the right hand side is what I'm putting over here, is the same region, same area, but instead of water majors and methanol majors, by the way, I should have mentioned the methanol majors are 6.7 gigahertz transition, and the water majors are 22.2 gigahertz transition. But on the right hand side, the star represents the hydroxyl majors, and this data comes from the MajorDB.net. Thanks Dmitry, and sorry, I should have mentioned MajorDB.net. So this is the 1665 and 1667 transition line, because those are the only two which are mostly or exclusively associated with the high mass star forming regions. There are rare cases where you see them otherwhere as well. So there, as you can see, there's much more targets that are available to me to look at and select my best 4 or 5 targets, which I can do astrometry and get some parallaxes, the same reason. So that's why the OH major becomes super, it enables a new tool to look at the regions which haven't been explored before. one of the other reasons is like, metallicity as well. Like, the outer you go in the Milky Way, there's like, these, you won't find that many molecules, or like, the methanol molecule or water molecule, but because of metallicity, you'll find these simple molecules as hydroxyl molecules. So it's very, it becomes suddenly OH molecule becomes suitable, or like an OH major becomes suitable candidate to do astrometry in outer spiral arms. Why this is perfect time? So that I'll just sort of tell you the story that how it all connects together. Right now, as you all know, there's this awesome survey going on in the Southern Hemisphere. It's called Gas Cap OH survey. PIs are Joe Dawson and Sherry Breen. More on this Gas Cap OH survey, Joe will give a talk on Friday afternoon. So please tune in for that. But just a couple of lines is that it's, as we just, I think earlier today told about, is that it's detecting OH majors in all 4 transitions, 1612, 1605, 67, 1720. But I'm more interested in 1605 and 1667. One thing that it'll do is it's going to significantly increase the OH major population in the southern skies with the sensitivity that it has. I have seen the data. Me and Beth, who's on the meeting as well, I hope. So it's the data looks amazing, and again more when Joe talks about it. So there's this. Like, on the left hand side, you see a plot where the the regions that been observed or like targeted in this gas cap OH survey. On the right hand side is you see there's plus sign is the new majors and the circle is the known majors. And if I have read it correctly, I think there were 19 majors in that particular. This is one of the test regions of the gas cap OH, and there was 19 known majors in this region, which are represented by the circles, but there's 26 new majors that has been found, which are represented by the plus sign over here. So that shows that how much the OH major population in the gas cap OH survey is going to increase. So that will be a awesome a catalog to then go and select these majors from to do astrometry. So my last or final why OH major astrometry is what I talked about. It suits better with the current and upcoming southern hemisphere radio infrastructure. There's more targets. The calibrators are more brighter. There's been recently been advancement in calibration techniques which enables that. There are challenges going at lower frequencies, dealing much more with the ionosphere. Scattering is one of the issues, but I'm gonna this is something that I'm happy to talk about in person or outside as well, but I'm gonna stop it over here. So yeah, thanks to all of you and happy to take questions.
Thank you, Jay. And do we have any questions? So I had a quick question.
Mm-hmm.
I wonder, and we may have had this conversation. I can't remember. It seems vaguely familiar. But with the water masers that you might potentially use to map out the galactic velocity curve, are you able to identify and potentially exclude any water masers that might be part of an outflow?
Sorry, so you're asking that the potential water major sources that I'm looking at the inner Milky Way or the regions that I'm interested in. You're saying that so generally the water majors, even the one that I looked, that I worked on, I as I one of my plot shows that it shows one side of the outflow. So I'm not sure what you mean by excluding it out. I wasn't planning to exclude it out.
Oh, I guess I'm again. It's not my area of expertise, so I'm a bit underinformed on this one. But I thought that water masers would tend to trace outflows and therefore might potentially be skewed significantly from the systemic velocity of their neighborhood.
So generally, what we what we do is that when we detect methanol, so the basic rule of thumb is that the centroid the central protostar's velocity is plus minus 5 kilometers per second towards the velocities you find for the your major and metal major. And for water majors, that jumps to 10 kilometers per second. Even though these water majors are in outflows, they are so the protostar is so young, and that their outflows they're still very close. Even in that they're in jets, they're still very close. That if you are tracking these water majors, you're still very close to the protostar. So you're not very far away.
Andre?
Such a question, Jay, that OH majors are in star-forming regions and evolved stars. When you have shown that the positions of the majors, how did you distinguish the star-forming majors from evolved star ones? Because for your case, the star-forming regions are necessary, but evolved stars are just something different.
Yeah, thanks for your question, Andre. So people can correct me over here. As far as I know and what I've studied in literature is the 1665 and 1667 line. Of course, there are some cases where these lines or these transitions have found in the evolved stars as well. But these mainly or generally these transitions are found towards the high mass star forming regions. So among all these within all those 4 transitions that I mentioned about that Gascap OH is going to do, I'm only looking in 1665 and 1667 transition, because that's what has been in literature it's been reported that it's after looking or it's in the high mass star forming regions at the very young stages. And I think the Dmitry was showing in his plots that after I think the water majors and then methyl majors, and then after that hydroxyl majors appears in the high mass star forming regions, and I think they are in circumstellar disk. Please correct me if I'm wrong, Dmitry.
Yeah, just the thing is that statistics is very good, but when you're measuring parallax, you're spending a lot of efforts on one single source. And in this case, you have to be very careful in choosing the target. So I wanted to draw your attention on the ways how to distinguish this.
Yeah, you're absolutely right. That's one of the big issues when allotting a telescope time is that because there's going to be a lot of time invested on that one particular source. So you want to make sure that it is doing what it is or you are looking at what you're supposed to look at. But I can't give you a number that what certainty I can say one particular 1665 transition is from the high mass star forming regions. I have to go read more on that, but maybe fairly with high percentage of certainty, I think it is coming from a high mass star forming regions. Yeah.
Dmitry?
Yeah, I want just to mention that problem of distinguishing between star-forming regions and circumstellar sources is already solved in MesoDB. So you have a column named type, and you can just type is evolved, and it is already filtered. So we base this classification using SIMBAT data. So it is quite exact, and mistakes are very rare. So you can just use it. Yeah, thank you.
Thank you, Dmitry. I actually did not know about that, and I'll go and further refine my list that I put in over there. Yeah.
Yeah, I can send you details as message.
Yeah, I will get in touch with you in person later on. Thank you.
Okay.
But in this case, we are talking about Gascap OH. Is this done for these sources, Dim?
Uh,
These are
you're
new
asking-
sources. GasCap OH is not included in MaserDB yet.
It is not still published. It's not published.
Yeah,
Yeah,
we
but
do
Jay is
not
talking
have.
about these sources, so you cannot distinguish this.
Of course.
Yeah,
When it
so-
will release, I will add it.
Yeah, so just to on that, yeah, of course, GasCap OS, we don't have catalogs as of now. That's still a bit far away, but of course, and when the catalog comes and then the classifications and whatever, I'm not 100% on that how you what needs to be done to classify whether it's evolved stars and HIMA star from region or something. But what I was more hinting at that future of OH astrometry. For the current one, if I want to do for next 5 years or so, there's already enough measures that I can found in MaserDB. And when I say next 5 years, so I'll say next 5 or 10 measures, because there's hardly people will have time over here in these telescopes to let me do astrometry more than 10 major sources. And that I have already enough of those in the MaserDB catalog. But that's a good question. Thank you, Andre. And I'll definitely, when the GasCap OS catalogs comes out, we'll work with Dmitry to for the further classifications of those, so that people can use them for these purposes.
So means are developed already by Dmitry. So you can use these for your GasCap sources probably. Is that correct, Dmitry?
It can be used when I enter data into database. So I can use it locally without publishing. So if you need it, I can do it.
So I suggest you cooperation.
Yeah.
Yes.
Can I ask
So-
something, Dmitry? This is just I'm curious, just from the last conversation. How is it exactly that you make the determination if it's a high mass star forming region? Is it the coincidence of certain species of maser? Is it profile types? Is it?
Actually, it is written in our water maser database paper. So in
Okay.
brief, we just cross-correlate all measure with Simbad database and find all sources that belong to class like Mira, OH, ER stars, and so on. And
Okay.
that's how we do it.
Okay. There is something that's in, say, a new survey and it doesn't align with anything. Are there secondary measures, or are you able to put unknown in the database?
Unknown, yeah. We have a small amount of unknown sources, and they are marked as unknown.
Awesome. Thanks for that.
And
Yeah.
something can come
And also,
from
there are a
theory.
lot of mixed sources.
Something can come from the theory. So Malcolm can say, for example, if 1612, what is the ratio between 1612 and 1665? Can this help to choose to tell between the star forming regions and the whole stars? Is that correct, Malcolm?
Yeah, so 1612 is much more common in the evolved stars, for sure. So for the main line as well. So yeah, I mean, if you basically you can get 1720 in some star forming regions, but it's almost never in lake type star.
So is it a possibility? So if you detect something at 1665, and you look for 1612, in this case, you can distinguish between star forming regions and evolved star. Is that correct?
Well, so spectrally, you probably could do that, because the 1612 in late type stars would tend to have this, sort of widespread double peak, which it wouldn't necessarily have in the star forming regions. So, and that just sort of comes from the spatial separation of the main lines from the 1612 in evolved stars. They sort of come from very different regions.
That's not 100%.
It's not 100% certain, but you know, it's a pretty good method, I think.
Just a good suggestion. Just good suggestion for Dmitry to calculate what is the probability. He's very good in this.
Yes.
Do we have any further questions? All right, then I might take a chance to thank our speakers again. So thank you, Dmitry and Jay. And thank you to everybody who participated in the discussion, and thank you all who came along to watch. I might take this opportunity also to mention, please forgive me if I mentioned at the beginning of the session. I've totally lost track of how many times I've said this today. On the main page of the website, I now have some lists that we've been compiling of people who are experienced at using different telescopes, using different codes, and also people who are either in charge of or have, again, a lot of experience with different surveys or databases. So I can encourage Dmitry, if you could add the Maser database to that list, that would be awesome. But also, if any of you have any other data sets or other types of surveys upcoming even, and would be confident and comfortable helping other people out with it, please add that to the list. And thank you very much, and I'll see you guys in the next session.
Thank you very much.
Thank you, Anita. Thank you, everyone.
Bye.
Yep,
So good to see you.
bye. Yep, bye.